In the last class, we have seen the rotation of the coordinate system, and we obtained a definition of vector, a more general definition of a vector quantity. Now, using that idea, we are moving on to the tensor analysis, and we define tensors, the tensor quantities, which are of extreme importance in physics. So basically, we use the definition of the vectors that we saw in the previous class for defining tensors. Scalars and vectors. These are vectors. Okay. We have two types of quantities, scalars and vectors. These are actually special cases of tensors. Okay, scalars and vectors, the two types of quantities that we encounter in physics, these are actually special cases of tensors. Okay, so what is a scalar? A quantity that does not change under the rotation of coordinate system. That is invariant under the rotation of the coordinate system. That is labeled as a scalar. Okay. So this quantity, the scalar quantity that does not change under the rotation of the coordinate system. Now we are referring to the rotation of the coordinate system for qualifying the properties of the scalar or the vectors. So a scalar is a quantity that does not change under the rotation of the coordinate system. Okay, we saw a vector changes under rotation of the coordinate system, and the transformation equations we know that we saw. But a scalar is a quantity that does not change under the rotation of the coordinate system, and it is invariant. It is specified by one real number. Okay, and it is said to be a tensor of rank 0. Okay, this is actually a tensor of rank 0. So scalar quantity, a scalar is a tensor of rank 0, and it does not change under the rotation of the coordinate system. Okay. Now what is a vector? That actually we saw. A vector is a quantity whose components transform under rotations, like those from the distance from a origin is called a vector. Okay, we have seen the position vector, how the components of the position vector transform, and we arrived at this relation. The definition of a vector vi prime in the rotated coordinate system, the components are vi prime, that is given by sigma j aij vj, where aij we know, which is dou xi prime dou xj. Okay, dou xi prime dou xj, or it can, in Cartesian coordinate system, you can write this like dou xj dou xi prime, both are same. Okay, so this is the definition of vector in an n-dimensional space. If we are considering an n-dimensional space, the components transform like this. Okay, where this aij is dou xi prime dou xj, or dou xj dou xi prime. Okay, so this is how we define the vector. In three-dimensional space, if you are taking three-dimensional space, vector is specified by three numbers, three real numbers, and we say vector is a tensor of rank 1. We say vector is a tensor of rank 1. Okay. So rank is 1. For scalar, the rank is 0. Okay, scalar quantity, that is actually a tensor of rank 0. Is actually tensor of rank 0, but this is a tensor of rank 1, and it has 3 components. Actually, in n-dimensional space, a tensor of rank n will have n raised to n components. Okay. So the number of components of a tensor, that is given by dimension n. Okay, n-dimensional space, and if its rank is small n, it will have these many components. So in 3-dimensional space, dimension is 3. If its rank is 1, this will be 3. So 3 components are there. Okay. So that's a vector. Now there are actually 2 types of vectors, or rather 2 types of tensors. In the case of vector which is basically a tensor of rank 1, we have contravariant vector. Any set of quantities transforming according to ai prime equal to dou sigma j dou xi prime dou xj aj. This is defined as a contravariant vector. Okay, ai prime equal to sigma j dou xi prime dou xj aj. This is called a contravariant vector, or a contravariant tensor of rank 1. Then what is a covariant vector? The other type of vector. Any set of quantities aj transforming according to this relation, ai prime equal to sigma j dou xj dou xi prime. Okay, dou xj dou xi prime. In the previous case it was dou xi prime dou xj. Here it is dou xj dou xi prime aj. Then it is called a covariant vector or a covariant tensor of rank 1. Okay, so we have 2 types of vector: contravariant vector and the covariant vector. This is how we define the vector, the 2 types of vector. In Cartesian coordinate system, both of these actually are same. Dou xj dou xi prime is equal to dou xi prime dou xj, which is equal to aij. We know that. And there is no difference between contravariant and covariant transformation. So in Cartesian coordinate system, this transformation, the dou xj dou xi prime, that is equal to dou xi prime dou xj. Okay. So there is no distinction between covariant and contravariant in Cartesian coordinate system, because these 2 are same. But in other coordinate systems, for example, a spherical polar or a cylindrical coordinate system, this is not the case. Okay. They are not the same. The contravariant and the covariant transformations are not same. Okay. Now, the covariant vector, it is denoted by a superscript ai. We use superscript here for covariant vector, and we use subscript I for the contravariant we are using superscript, and for the covariant we are using subscript. Okay. So that is the notation that we use, but in Cartesian there is no difference. Okay. Now we have defined what is a scalar. Scalar is a tensor of rank 0. Then we have defined a vector, a tensor of rank 1. Now we are in a position to define a tensor of rank 2. Okay, this is a tensor of rank 2. So here the components of a tensor of rank 2, a prime ij, that is given by this sigma k l, summation over k and l. I, j, c, they are in the superscript because it is a contravariant tensor. So we have dou xi prime dou xk, then dou xj prime dou xl, akl. Okay, superscripts clearly show it is a contravariant tensor. Then we have covariant tensor of rank 2. We have c prime ij, c we are using subscripts, summation over k and l, dou xk, dou xi prime, dou xl, dou xj prime, ckl. Okay, so this is a contravariant tensor of rank 2. Mixed tensor of rank 2. What is a mixed tensor? We have both the covariant index and contravariant index. See here we have I, which is the contravariant index, and j, which is the covariant index. Okay, and this is dou xi prime dou xk, dou xl, dou xj prime. See, since j is a covariant index, I am using dou xl, dou xj prime. I is a contravariant, so I am using dou xi prime dou xk. Okay, so we have a mixed tensor of rank 2. So this is how we define mixed tensor of rank 2. Okay, if you are using, again we are saying this, if you are using Cartesian coordinate systems, all three forms of the tensors, whether the contravariant, mixed or covariant, all are the same. Okay, for Cartesian coordinate system, there is no such distinction. Okay, that we have seen. Now, the importance of the tensor analysis in physics is the transformation laws for the components of a tensor that give us quantities and properties that are independent of the choice of the coordinate system or the reference frame. Okay, these transformation laws that gives us entities which are independent of the choice of the reference frame. This independence of the reference frame, invariance, this is ideal for expressing and investigating universal physical laws. Okay, in physics we need laws which are independent of the coordinate system. And these transformation laws help us to define quantities or the properties which are independent of the coordinate system, because we always have the transformation relation, the transformation laws are there, and this makes the tensor analysis important in physics. Okay. Now a second rank tensor in 3 dimension. Okay, if you are using 3 dimension, it can be conveniently represented by a square array. See here we have a square array, second rank tensor, A11, A12, A13, A21, A22, A23, A31, A32, A33. So we know what the dimension is 3 and the rank is 2. So how many components will be there? 3 raised to 2, 9. You have seen the definition. If the dimension is capital N and if the rank is small n, there will be n, capital N raised to small n components. So there for a tensor of rank 2, which is defined in a 3-dimensional space, we have 3 raised to 2 components, 9 components. It can be represented like a square array like this. So the most important point is, this does not mean any square array of functions, form a tensor. Okay, if you simply take a few quantities and write it as an array like this, it will not form a vector. The essential condition is its components should transform according to the transformation equations that we have seen for the various type of quantities. various type of tensors. So it has to, these components have to satisfy that transformation equations. Only then this can be called as a tensor. Okay. Now let's see tensors of rank 3. This is a tensor of rank 3. See, A prime I j k, this is actually a contravariant tensor of rank 3. And it is simply an extension of how we defined tensor of rank 2. The only thing is we have two indices, so dou xi prime, dou xl, dou xj prime, dou xm, dou xk prime, dou xn, ALMN. The covariant components like this, and the mixed tensor, dou xi prime, dou xl, dou xj prime, dou xm, dou xn, dou xk prime b, Lm, n. Okay, so this way we can define tensors of higher and higher ranks. Okay, the only thing is, for a contravariant index you write it in one fashion. For covariant index you write it in another fashion. That is the only difference. So we have tensors of higher ranks like this, and you can easily define like this. Okay. Now we show that the components of gradient of a scalar function. Okay, we are having a scalar function phi, and we have to show that it is transforming as covariant vector. Okay, it satisfies the transformation relations for covariant vector. So phi is a scalar quantity, and del phi, if you take del phi, then it will be a vector. Del phi is a vector, and we have to show it transforms as the components of the vector transforms as a covariant vector. Okay. So phi is vector quantity, function of x, y, z, x1, x2, x3. Phi x1, x2, x3, that is phi prime, x1 prime, x2 prime, x3. Why? Do you know why we have written like this? Because this is a scalar. Scalar, does not depend on the coordinate system. So x1, x2, x3, that is one coordinate system. x1 prime, x2 prime, x3 prime, that is another coordinate system. And it does not depend upon the coordinate system because it is a scalar. Del phi is a vector, and its components are given by dou phi dou x1 I, dou phi dou x2, dou phi dou x3. So these are the three components of the del phi. Del phi now becomes a vector, and its components are written here. And its components in the rotated coordinate system. The rotated coordinate system is this: x1 prime, x2 prime, x3 prime. There, how it is written? The components are dou phi prime, dou x1 prime, dou phi prime, dou x2 prime, dou phi prime, dou x3 prime. Okay, these are the components in the rotated coordinate system. Now, suppose I take dou f prime, dou xi prime. I am taking dou phi prime, dou xi prime, any of these components. This is equal to dou phi, dou xi prime. Why? Because phi prime is phi. But phi, we know that is a function of x1, x2, x3. Okay, phi is a function of this. So, dou phi prime, dou xi prime, that is given by, since phi is a function of x1, x2, x3, I have to write like this: dou f, dou xj, dou xj, dou xi prime, summation over j. Okay, dou phi, dou xj, dou xj, dou xi prime, summation over j. Okay. So this is now, if you compare this with the transformation, the transformation, what is it? AI prime ai prime equal to sigma j dou xj dou xi prime aj. This is the transformation relation for a covariant vector. So this is exactly in this form, dou phi prime dou xi prime, that comes in the position of ai prime. Similarly, dou phi dou xj comes in the position of aj, and see, these are same. So we can say the components of gradient of a scalar function transform as a covariant tensor. Okay, so let's stop here.